I'll start the recording. We are now in section 13.4. We're continuing our study of vector calculus, and we're looking at Green's theorem. Now, what is Green's theorem? All right, well, let me bring the down a little bit, and I already even have it highlighted. So Green's theorem gives the relationship between a line integral around a simple closed curve C and a double integral over the plane region D bounded by C. See figure 1. All right, let me show you figure 1 here. Okay, so there in figure 1, you have a curve C that forms a closed path around a region D. Okay, and they mention here that we assume in the highlight above there, we assume region D consists of all points inside C, inside that curve C, as well as points on the curve C. And in stating Green's theorem, we use the convention that the positive orientation of a simple closed curve C refers to a single counterclockwise traversal of the closed contour C, of the closed curve C. Okay. Thus, if C is given by a vector function R of t, you know, that'll trace out a space curve. That'll trace out the space curve C. If C is given by that vector function R of t, then the region D is always on the left as the position vector traces out C. So in other words, if you look in figure 1 there, pretend you're walking along the path, that curve, and you see though that arrow there. You see that arrow there near the on the bottom part of the path. If you were to walk in that direction along that curve, that closed curve, the region D would always be on your left. Okay, your region D would always be on your left as you walked along the path. That's called positive orientation. Now, if you were to walk the other direction, okay, so, and positive orientation, by the way, is in the counterclockwise direction. Okay, now the clockwise direction, if you went the other direction, you'd be moving in the clockwise direction. And clockwise direction would be what kind of orientation? It wouldn't be positive orientation. Moving clockwise direction along the curve is negative orientation. That's right, Kino. That's right. So remember that now, up to now, right? Let me just hold on. Let me bring up the whiteboard so I can give you some perspective here. Hold on, where is my stylus? Where'd it go? Hold on, I had it. Give me one moment, class. Oh, gosh, I gotta find my stylus. Oh, here it is, okay. Okay, so in section 13.2, you learn that the work that a vector field does in moving particle along a path in the vector field is given. It's given by this line integral. And if we were to write this out, okay, in some detail, and we talked about why this is true. This is how you would compute the line integral using this formula here. How many had some practice using that formula on the homework that was due today? How many had some practice utilizing that? Okay, Ellie and Kino, good. All right. I hope, you know, all of you will at least before the exam, right? And again, the late extensions on the homework last until tomorrow at noon. So, you know, do work on that. And this is good. We have a way that to compute the work. And this definition would work if the vector field, no matter what the vector field is. Now in section 13.3, we were able to compute this kind of work using the fundamental theorem of line integrals. But that relies on having a conservative vector field. We can't always assume our vector field is going to be conservative, and many times it won't be. So this is the most general way to find the work. So anything that we can do to help us find the work in an easier way is great, because of course the one thing that does make this challenging is, you know, you're computing an integral, and you have to, in order to get r prime of t, you need to find the parameterization of your path, and that in itself can take some time, right? A little time to do. So if we had a way, you know, we're very interested. What I'm trying to say is, we're very interested in finding ways to compute the work that a force field does in moving a particle along some path. And if the way to compute the work can be general, in other words, it would work for a general vector field, whether it's conservative or non-conservative, that would be great. And for closed paths, Green's theorem gives us a way to find this work. So Green's theorem. Let me bring it up in the book here. Now, so again, Green's theorem is for when the path is a closed path, and you have positive orientation. But of course, if you have negative, well, and you have positive orientation. Okay, so what is Green's theorem? Well, let me go down here and show you. By the way, in Figure 2, here are two more curves. Well, on the left, you have a curve with positive orientation. On the right, you have a curve with negative orientation. On the left, the curve goes traversing around the curve. You're going counterclockwise on Figure 2A. Figure 2B, you're going clockwise, and that's negative orientation. All right. So here's the Green's theorem. Green's theorem says, suppose you have a positively oriented, piecewise smooth, simple closed curve, and you will be having those kind of curves in here. Suppose you have that kind of curve in a plane. Let D be the region bounded by the curve. If P and Q have continuous partial derivatives on an open region that contains D, then Green's theorem is below. Now, they make a note. Recall that the left side of this equation is another way of writing the work. The integral, the line integral of f dot dr over your curve C. That again is the work that the force field does in moving the particle along a path. But in this case with Green's theorem, we were focused on closed paths. Well, if your path is closed, then Green's theorem is a way to compute the work. Okay. All right. And are there any questions on this? We'll look at some examples. Okay. But the proof of Green's theorem, they talk about it in on page 935 in your book. Green was actually, George Green lived from 1793 to 1841. He worked full-time in his father's bakery from the age of 9 and taught himself math from library books. I'm reading a biographical note here on him. In 1828, he published an essay on application of mathematical analysis to the theories of electricity and magnetism. And what happened was, at age 40, Green entered Cambridge University. You know, they felt, you know, he had promise, obviously, but he died 4 years after graduation. You know, they didn't, of course, have the medical ability that they have now. But the point is, I want to tell you a little bit about the man, and this theorem is named after him. Now, and you're welcome to look at the proof. The proof's there in the book. But let me ask you this. Let me go to the whiteboard here. You know, very important, this material. You know, Jeff Bezos would have not gotten to space without George Green, right? All these theorems are used. So this on the left is equivalent to this. Again, I'm talking about Green's theorem now. For computing work. See, Newton invented calculus in the 1700s, right? So in the early 1800s, see, because of that, that helped Green, of course, come up with this theorem, because it involves calculus, right? Hold on, let me just make this a little nicer. I don't know, sometimes it goes a little wacky on me here. Hold on. Okay, let me do this again here. Better. Oh, come on now. How many have had a professor, maybe the notes are not very legible? Has anybody ever had that experience? Well, mine are going to be legible, right? Okay, Kino knows what I'm talking about. Wow, okay, Juliana too. All right, all right. Okay, that's a P there, okay. I'm sorry, class, I'm a little bit picky about how things look here. Okay. Now, and of course, the vector field F is Pi plus Qj. Now, and incidentally, also, C is a closed path. So here's Green's theorem, okay, and my question is this. If the vector field F is conservative, what do we know? What do we know then about the partial derivative of Q with respect to x and the partial derivative of p with respect to y. What do we know about those derivatives when we have a conservative vector field? And of course, q and p come from your formula for the vector field. That's right, Ellie, they're equal. Very good. And you notice the partial derivative of q with respect to x shows up here. The partial derivative of p with respect to y shows up here. So in a conservative vector field, okay, like let's say, you know, you have a starting point here. What's a very easy conservative vector field that we've talked about? A very easy example of a conservative vector field that we're all living in. And it's why we can't go out to space, right? Easily. What vector field are we living in? Gravitational field. That's right, Yunu. So if we're in a gravitational field and I move along this closed path here, okay, I'll just make it a simple closed path. Okay, and you notice I went in the positively oriented direction. What work did I do? What work did I do in moving along this path? That's right, Charles, 0. Because along this path here, gravity acts against me going, you know, if I go along this closed path from, I'll try to, you know, from here to here, gravity acts against me. Work is negative. Gravity is doing negative work. But then if I complete the rest of the path, there, gravity's helping me go downward, and so the work is positive. So the net value of the negative and positive work is 0. So, so that's just an example. So any closed path in a conservative vector field, the work should equal what? For any closed path in a conservative vector field, what is the net value of the work that the vector field does in moving the particle once around that closed path? That's right, Ellie, 0. And given this criteria here, that the partial derivative of q with respect to x equals the partial derivative of p with respect to y, in a conservative vector field, in Green's theorem, what would your integrand equal for a conservative vector field? Here's the integrand right here. What's that going to equal? What's this going to equal in a conservative vector field? The difference between these partial derivatives, which is the integrand in Green's theorem and for the double integral. What's that equal to? Think about the criteria here. Think about this criteria. That's right, Juliana, 0. That's right, Ian, 0. And what's the double integral? What's the double integral? What's the double integral of 0 equal to? Well, let me ask you this. Okay, hold on. The double integral of 0, if this is what you're computing, okay, this here is volume, right? Remember, double integrals are, this is the volume between, this is the volume between blank and the XY plane. So hold on here. So to answer this question, it's helpful to think about so if you have the double integral of 0 dA, and 0 is your function of x and y, this double integral would be the volume between z equals blank and the xy plane. Z equals what? What are we going to put here? Zero. That's right. Well, what is z equals 0? What is z equals 0 in three-dimensional space? That is the xy plane. So what's the volume between the xy plane and itself? The volume is going to equal 0. That's right, Ian. So you see, Charles, I don't even need to do double integral here to compute this, because I know that what the double integral, what the double integral geometrically represents, and or we know that, and so this is going to equal, this double integral is going to be 0. Okay, so sometimes what happens is, Charles, does that make sense? I want to make sure. Is everybody comfortable? Excellent, excellent. So a lot of times, good, excellent, Malik. Wonderful, Madeline. And a lot of times people, Green's theorem is a little hard for people to maybe remember. Of course, you'll have access on your, to the book on the final exam, right? But I always, it helps me to remember it just by this kind of idea that if I have a conservative vector field, the work is equal to 0 for the closed path. And okay, well then this has to be the partial derivative of q with respect to x minus the partial derivative of p with respect to y. That has to be the integrand, right? That has to be. It can't be, because by virtue of the fact of what the criteria for a two-dimensional vector field is. How many found, was this helpful to kind of help you feel a little more comfortable with Green's theorem? Are you a little more comfortable with it? Maybe give me a thumbs up if you're okay. Kino's good. All right. All right. Well, let's. And Charles is good. Wonderful. Wonderful. Sometimes, proofs are nice, but making connections is nice too. And so that's what we're doing here. So okay, let's go to an example. I'm going to go right to an example here for your notes. Let me just see here. Okay, let me give you a moment to copy this example down, okay? Okay, so here we have a particle that starts at the point -2, 0. It moves along the x-axis to the point 2, 0, and then along the semicircle, y equals square root of 4 minus x squared to the starting point. So remember, y equals square root of 4 minus x squared. Okay, if we square both sides, I mean, we know this is just, well, it's positive, but if we square both sides, we'll get y equals 4 minus x squared, or x squared plus y squared equals 4. And that's a circle with radius 2. But of course, because y was equal to plus square root of 4 minus x squared, this would be just the top half of the circle. What we want to do is we want to find the work done on this particle by this particular force field. So, you know, I could try to use section 13.2. I could use the definition of work to, you know, that line integral definition of work to compute the work. I could, that would be 13.2 approach. Section 13.3 approach would try to see if the vector field is conservative, and that if it is, use the fundamental theorem of line integrals. But I know section 13.4 using Green's theorem, and I can use Green's theorem because I happen to have a closed path here. That I can apply that theorem without really, I mean, I could just apply that theorem, you know, quite nicely. May I go to the solution here? Does everybody have this copied okay? Maybe give me a thumbs up if you're good. Excellent, excellent. Okay. Wonderful, wonderful. Okay. Let me ask you this. What's the first thing we should do for this problem, you think, to get us started? I mean, what might be a nice thing to help us kind of feel comfortable? What might be a good way to start the problem? I mean, we know Green's theorem is going to involve a double integral, right? And whenever we have a double integral, we have to have limits. We have to have limits for a double integral. And to get the limits, what do we need to really have an idea of? The blank D. First word begins with an R. Okay, first letter, I should say. All right, one word. Then we have an E. Second letter is an E. Man, nobody plays Wheel of Fortune here? Watches Wheel of Fortune? All right. Third letter is a G. Let's draw a picture of the, all right, fourth letter I. There you go, Ellie, the region D. Okay, all right, so I just want to draw the region D here, and I know the path that the particle takes. So here's the path that the particle takes. It starts right here at -2, 0, moves from -2, 0 to +2, 0, right? And then it moves along that semicircle. Okay, and we know, is the orientation here positive or negative? Positive orientation, right? So C is that curve, our curve C, is positively oriented. So, okay, here's our vector field F for this problem. And since C is a simple, closed, positively oriented curve, the work done by the force field, vector field F, in I should say, hold on here. The work done by the force field F in moving the particle, once around this path C, is given by the Green's theorem, which I wrote down there. Let me give you a moment to copy this. Okay, so here's the Green's theorem. And are there any questions before we move to the next page? I'll ask you a question. If we were to compute the work, okay, if we were to compute the work, using the definition of work that you learned in section 13.2, how many integrals would we have to, well, if we were to do it this way, using section 13.2 to compute the work, how many integrals would we have to have? In other words, let me rephrase it another way. Okay, using the definition of work in section 13.2, could we compute the work with just one integral? If we were to do this problem using section 13.2, well, hold on, Ian. Let's look at the path. So the first part of the path, I think you'll agree, is a line segment, right? First part of the path is this line segment. So we could call that C1. Hold on. Let me put it over here. We could call that C1. So we'd have one line integral across C1, but would we need a second line integral? Would we need to find a second line integral? We would. That's right, Ellie, because here in blue is the semicircle. So that's your C1. So in other words, C, this C here, is equal to the union of C1 and C2, right? Put the C1 over C2 here. This curve C, this closed path C, is equal to the union of C1 and C2. So if you're going to use section 13.2, you'd have to get the parameterization of each of those curves separately, and compute the line integral for each of those curves and add them. And that'll get you the answer. So you can do it that way, but Green's theorem will be a lot easier. Okay, it'll be easier, let's put it that way. Okay. Okay, are there any questions on that? All right, well, let's apply Green's theorem. So here we go. So Green's theorem, the work, to find the work. Okay. X is equal to P. X cubed plus 3xy squared is equal to Q. And you notice in the double integral, I don't commit to my limits yet. I don't state, am I going to integrate with respect to rectangular coordinates or polar coordinates. I don't worry about that yet. First thing I want to do is I want to, get down to here. I want to get down to this step here. Okay, take a moment. If you have any questions, let me know. Okay, so now that we get down to this step here, this third step, or I guess fourth step, now it's time to decide what we're going to use for our coordinates. And because we had a semicircle, oh, that's half a circle, but clearly, I mean, normally when you have a circle or half a circle or a quarter of a circle, you use polar coordinates will be easier. And so if I go to here, here's my region D right here. It's encased by a semicircle of radius 2. Okay, what would theta be, by the way? I mean, for this region D, okay, the region D here. Hold on. So my limits, well, I mean, for my region D, okay, the radius values in region D go all the way from what? Radius would be between what values? What are the values of my radii? 0 to 2. Anywhere on that region. Good, thank you, Ellie. What about theta? What would theta be between? Zero and pi. Good, that's right, Juliana. So let me just write that in. 0 and pi. So this is, you have to be very careful with these kind of problems. And then on the exam too, the exam you're going to be taking, you have to read the problems carefully and, so you get the right limits. So, here you go then. This is our double integral. Since we're integrating with respect to polar coordinates, the dA is r dr d theta. That's your dA. And, I'm going to start my iteration here. Please let me know if you have any questions before we go to the next page. Okay, Charles is feeling good. Let me ask you, could this integral here be brought out in front of the first integral? It could, definitely it could. And that's because this inner integral here is a value, right? It's equal to a number, and numbers can be brought out in front of integrals. Okay, so that's a handy trick sometimes. Now, naturally, it doesn't work all the time. It doesn't work all the time, but I can bring that integral out, and maybe I'll bring it out. Maybe I'll bring this integral out and put it right here, right? So are there any questions? Are we ready to go to the next page? Just give me a thumbs up and we'll go to the next page. Okay, excellent Malik, excellent Kino, excellent Noah, excellent Ellie, excellent Madeline, Okay, wonderful. And you notice, class, in the work here, thank you, Juliana, thank you, Hunu. You kind of notice things too. So like 3x squared plus 3y squared, I'm going to write that as 3 times x squared plus y squared, right? I'm going to factor that 3 out, okay? Because I know then, x squared plus y squared is r squared. So, okay, well, moving on here. All right, so here's the integral, double integral we had. And I bring that inner integral out in front of the outer integral, okay, because it's really just like bringing a number out, and we get then the product of 2 integrals. And when we work that out, we should get 12 pi. And that's the value of the work. And that means that this vector field helps the particle move along that closed path. And you have a program, remember, one of your MATLAB programs shows you how to plot a curve on top of a vector field. Now, obviously, you have to adjust the program, and I guess for this curve, you would need probably 2 curves you put together, right, to draw that entire closed curve. You would need to have in MATLAB, you would need the parameterizations of both curves. And you have to graph both curves, use a hold command, and then another hold command, and then a vector field. But you can do it, and you would see that the vector field overall helps that particle move along its path. Okay, I'll give you another moment to copy this down. Let me know if you have any questions. All right. All right. I want to go to the example, and I want to go to the ebook and look at a few, just one or two things there. By the way, if the particle were moving around the path in the clockwise direction, in other words, if the path had negative orientation, what would the value of the work be if the particle had a negative orientation. That's right, Charles. It would be negative 12 pi. So in these problems, sometimes they'll say in the problems, they'll say there's negative orientation, or if you know, it's important. It's important when you draw. Let me go back to the picture here. It's important that when you draw your path, you know, as described by the problem that you're given, that you notice the orientation, because sometimes the orientation could be negative. Okay, and so you just want to keep that in mind. All right, well, let me get the, hold on, let me get the ebook here. Hold on here. One moment. Okay, let me get the ebook. Okay, so sometimes with Green's theorem, it can be used also to evaluate a line integral that would be impossible to evaluate using the other, you know, using like the definition in section 13.2. So in example 2, by the way, that circle, you see that circle on the integral there in example 2? The circle that they draw on there means that the path is positively oriented. That's what that circle notation means there. And this line integral, and really what you're doing is, you know, you're adding a line integral with respect to x and a line integral with respect to y. You're adding them together. That's what that means. That notation where they have that line integral over the curve c. But let's just call it a line integral. So you want to compute that line integral, or the sum of the two line integrals, one with respect to x, one with respect to y, in example 2, where c is the circle x squared plus y squared equals 9. So in this problem, you have, if you use Green's theorem, you can actually evaluate this. So here, let's take a look. So in the solution, the region D bounded by that circle is the disk. So let's go to polar coordinates. Okay, and they do so. But they don't yet. You know, they first of all, like if you look at the, I mean, here's the highlighted work here. They first of all, well, let me see here. Hold on. Okay, so in the second line, the double integral over the region D, the first partial derivative with respect to x would equal 7, right? And the second part, and then the first partial derivative with respect to y that you see there, that would equal 3. Okay, and are there any questions on the what you're seeing there? Who's feeling good? Maybe give me a thumbs up if you're feeling good about that. Okay, Malik, good. All right, Kino, Ellie, Charles, Madeline, wonderful, wonderful. Juliana, excellent, excellent. Okay. I'm just looking at one thing here now. Okay, let me show you something else here in the ebook. Here's that information on green that I read. Okay, to you. Okay, so Green's theorem has extended versions as well. Okay, Green's theorem has extended versions. So let's say, let's take a look at figure 6. Okay, let's take a look here at figure 6. In figure 6, you have a curve C1, a curve C3, a curve negative C3, and a curve C2. And we can look at the region D as the union of two simple regions. Okay, so I want to say this the right way. So, although, although we have proved Green's theorem only for the case where D is a simple region, we can extend it to the case where D, the region D, is a finite union of simple regions. A finite union of simple regions. So what they do here is they have this sort of pretzel-shaped solid, and in figure 6, and it's composed of two simple regions, D1 and D2. So the region D1 is found by taking the union of the curve C1 and C3, and the region D2 is surrounded by the union of the curves C2 and negative C3. Okay, and so we can use Green's theorem on each of the simple regions, D1 and D2. And I wish I could kind of show this all, but this would be the the line integrals for C1 union C3 and C2 union negative C3. Okay, but if we go back to the figure here, figure 6, if you wanted the line integral over the curve C, that would be the, hold on here. One moment. Yeah, if you wanted the line integral over the union of the curves C1 and C2. The union of curves C1 and C2 would be that entire path, that entire red path. All you would need to do is add up the two, hold on here, it's a little bit, you would just add up those two line integrals above. So hold on here, let me take this off. I'm talking here. I just want to highlight it. Put that in pink. So if we add the two equations, the line integrals along C3 and negative C3 will cancel. Okay? And that would give you then, this expression in the highlighted box using the Green's theorem. So just give me one moment here. Hold on. Yeah, so we're going to be sticking, hold on one moment, class. Okay, I want to say this the right way. So you see, the issue is that you have to just forgive me. I want to make sure I say this the right way. You're able to, this region, this figure 6, the region like C1 and C2 separately enclose simple regions. Okay, they separately enclose simple regions, but the entire path C1 union C2 would not be a simple region. Okay, and so in order to compute the line integral, the work along the entire path where it's the union of C1 and C2, what you have to do is apply Green's theorem to the path C1 union C3 and apply Green's theorem again to the path C2 union C negative 3. Okay, you would apply it to both those. You would apply it to both those paths. But what happens is the line integrals with respect to C3 and negative C3. If you think about the definition of line integrals, though, like the formal definition, if you were to find the line integral along the path with C1, the C1 union negative C, sorry, the path with C1 union C3, you would be using the definition of the line integrals in section 13.2, you would be adding two line integrals, one for C1 and one for C3. And then if you were to find the line integral along the path for C2 union negative C3, you would be adding two line integrals as well. Line integral for across C2 and the line integral across negative C3. But the point is that the line integrals for C3 and negative line integrals for C3 and negative C3 would cancel each other out. And so effectively then the line integral across that across the line integral for C1 union C2, we could apply Green's theorem for that. It effectively allows us to extend Green's theorem to regions that are not simple. Okay, that's the idea. And if you look down here in figure 7, they give you even a more extreme example of that. So I'm thinking about other classes where you're going to apply Green's theorem, and you know, it would be useful to be aware of this. Okay, and they give an example. They give an example. Well, first, are there any questions on that? To understand it, to really understand it in comfortably, you have to remember like how when you originally learned line integrals, if you had a curve that consisted of two different, the union of two different other curves, you found the line integral for the entire curve by adding up the line integrals separately. And that's the connection that you have to make in order to feel comfortable with this. Are there any questions on that? All right, well, let me show you an example here, okay? Let me show you an example. So in example 4, okay, they want you to evaluate this line integral, which remember is really the sum of a line integral with respect to x and a sum of a line integral with respect to y. They want you to evaluate that where C is the boundary of the semi-annular region D in the upper half plane between these two concentric circles. Okay. So the region D is the region D. If we look at the figure here, gosh, I got too much open here. Hold on, let me just close this out here. One moment. Clicking on too many things here. All right, so the region D is here. Okay, and that is not considered a simple region. If you, I mean, the idea here, you know, why isn't it simple? Let me give you a reason here, kind of a simple reason. How many have to take electromagnetism? How many have to take a class in that, or have taken that, seen that in their travels? Okay, Charles and Juliana. All right, very good, very good. So in example 4, section 13.4, and I'm sorry the picture's not the best. Okay, I'll try to, you know, I'll try to draw it a little bit better here. Hold on. Okay, so that's okay, right? All right, so that's your path C. Okay, and the particle is moving along this path here, okay? But you see, if you picked a point over here and then a point over here, you could connect a line between the points, and the line falls outside, the line here falls outside the region D. The line falls outside the region D here. Okay? So this is not a simple closed, this is not a simple closed curve. Okay? But if you have a curve like this, okay, if this is your curve, then any point inside the, you know, and again, here's the region D enclosed by that curve. Any point inside, well, if you pick any 2 points inside that curve in the region D, the path or the line segment connecting those points always falls inside the region D. So that's what we mean here. This here is simple, a simple region D. Simple region D. This here is, hold on here. This is not simple, not a simple region D. You see the difference, class? But by virtue, okay, good. Thank you, Juliana. Thank you. But Green's theorem can be extended to handle not simple closed regions D. It can be extended to handle that. Because if we go back to the ebook here, thank you, Charles, thank you, Juliana. If we go back to the ebook here, okay, they justify with figure 6 and what we just talked about above. They justify that, and again, this figure 6 is not a closed. This is not a. Hold on. This figure 6 here is not a simple. The region inside is not a. Sorry, I want to get my phrasing right. Yeah. I should have said the curve. Let me just make sure I had this right. Hold on. Let me go back. I've got to make sure I got this right. One moment. Okay, so there's an example where connecting 2 points in the region D along this, inside this path, where the line, the line connecting the region, the 2 points, that line falls outside the region. So this is not simple. Hold on here. Let me make sure I got this. Let me make sure I got this terminology right here, okay? Yeah, so right, the region D is not simple, okay? But then the other region D, like this here, okay, so along that path in the region D, you can connect any 2 points, and there, the path, or the line segment connecting the 2 points falls inside the region D. So this is simple. Okay, so that's what I had said. And the point is here is that when we look at Green's theorem for a path for a region D, which is the union of D1 and D2 in figure 6, that is not simple. Well, Green's theorem can actually handle that kind of situation. It can handle it, okay? Because if you look at what they have above here, if they look at what they have above, okay, the C1 union C3, which encloses region D1 in figure 6, and then C2 union negative C3, which encloses region D2, okay, those, if you look at the Green's theorem here, we apply Green's theorem to both of those closed paths. But by the definition of what computing line integrals means from section 13.2, we know that the line integral of C1 union C3 can be written as the sum of the line integral across C1 and the line integral across C3. And the line integral of C2 over C2 union negative C3 can be written as the line integral of C2 plus the line integral across the negative C3. Okay, and what happens is when you add those two line integrals up, the line integral over the C3 curve cancels out with the line integral over the negative C3 curve, right? Because the t limits would be switched. Okay, and therefore you have it then that, see, they say that if you add the two line integrals, okay, the line integrals along C3 and negative C3 cancel, and so we end up getting then the line integral across C1 union C2, and that just is equal to then the Green's theorem. So it allows us to be able to work with paths where the closed path contains a region that is not simple. Okay, does this reiteration help you understand? Is this helping you understand what we're doing here? Was this helpful? Maybe give me a thumbs up if you're okay. Good. So more people are comfortable. Good. I want you to be comfortable. Thank you, Juliana. Thank you, Ellie. And so when we come across this example 4 here, where we want to compute the sum of these line integrals, which is really the work that the force field with components y squared and 3xy does in moving the particle along the path defined by that region D. And what's that path look like? Well, here it is. And in figure 8, and that's clearly not a simple region D, but nevertheless, we can just apply Green's theorem to it. I mean, it's absolutely amazing, absolutely amazing. So, you know, when you do the work, well, region D, you know you're going to be using polar coordinates for that, for the double integral for region D, and so you just apply the Green's theorem, and there you go. There you go. So they, and you get 14/3. And Green's, are there any questions on that? Who's feeling good so far? Maybe give me a thumbs up if you're good. Malik's good, meaning you're understanding. All right, Juliana and Ellie, and okay, great. And you know, Green's theorem, they mentioned that Green's theorem can apply to regions with holes. Okay, it can hold on here. Green's theorem can apply to regions with holes as well. Okay, and they talk about that. They talk about that here, you know, and you know, this would be like figures 9 and figures 10, and you know, we're not going to delve that deeply into it, but you know, I'll let you look at that. But are there any questions at all? Any questions at all? I just want you to be aware of Green's theorem and how it's really applicable to a lot of situations. You could see it in an upcoming class, and I wanted to be sure that that you're comfortable. Okay, if there are no questions, I'll stop the recording.